Hello and welcome to my lightning talk. My name is Fabian Rohden, and in this talk I want to present to you my idea on how viruses could be blocked from gaining drug resistance through evolution. First of all, what are antiviral drugs? After vaccines, antiviral drugs are our second line of defense against viruses. Unfortunately, vaccines are not always available for every viral infection, and even if they are, they may not offer complete protection. Vaccinated people can still experience severe diseases, facing hospitalization or even death. Furthermore, infection can have negative long-term effects, as a current example of long COVID shows. Antiviral drugs can help to stop the virus faster and reduce the potential for long-term effects. Now, my story would end right here if it wasn't for evolutionary escape. This is a mechanism that helps viruses to overcome drugs. An antiviral drug targets a part of the virus that is essential for virus production. A good target are viral polymerases. These enzymes copy the genome of the viruses. However, once a drug blocks the virus, this puts evolutionary pressure onto the virus to find a mutation to escape. A mutation that renders the drug unfunctional whilst keeping the polymerase functional, also at low efficiency. Due to the natural selection of evolution, only viruses having such a mutation will survive the drug treatment and will then multiply again. The bitter irony is that using antiviral treatments is also the most efficient way for viruses to become resistant against such treatments. The current method to combat viruses is to give patients a drug cocktail consisting of 2 or more drugs. The drugs target different parts in the viral replication machinery. Such a cocktail can often be sufficient to knock out the virus. However, such different drugs need to be developed first. Furthermore, a cocktail does not prevent the emergence of resistance mutations against the respective drugs. After having had a few cocktails myself, I thought how an antiviral cocktail would need to be mixed in order to prevent evolutionary escape. Instead of going after different targets, the cocktail would need to contain 2 or more drugs that all aim at one target. In such a way, the combined resistance mutations reduce the efficiency of the target to 0. This way, either the drugs work or the mutations are too much for the virus, leaving no option for evolutionary escape. So, how is it possible to find out whether 2 drugs will be able to prevent evolutionary escape or not? I think it can be done by a method called network analysis. This is a computational method that can create mechanistic models of proteins, like the viral polymerases, and show how they function internally. To do this, one first needs a 3-dimensional structure of the target protein. And thanks to science, such 3D structures are publicly available online. The static structures are then used as input for the second step, molecular dynamic simulations. These simulations mimic real world and its physical laws to produce data on how a protein moves over time. In easy terms, I put the protein in a box of liquid and watch it floating around. In step 3, I can use the collected floating data to create a contact map of all amino acids, the basic building blocks of every protein. This contact map shows me how all the amino acids interact with each other, and as a final step, I can cluster them together into bigger communities, like identifying several parts within a car as being part of a larger compartment, like the motor. With these communities, I can show how a drug, upon binding to the polymerase, creates a mechanical signal that gets transferred through the polymerase towards the active site, where the copying of the genetic information happens. A mutation allowing evolutionary escape must be along the signal pathway of the drug. The mutation interrupts the signal and keeps the active site of the polymerase safe. However, the mutation itself changes the overall dynamic behavior of the polymerase, and can negatively affect the mechanics of the polymerase. My hypothesis is that combinations of resistance mutations can be used to achieve overlapping inhibition. If the virus develops only one mutation against one of the 2 drugs, the second drug will inactivate the polymerase. In case of the development of both resistance mutations at the same time, the combined structural changes could themselves turn the active site into an inactive state. Therefore, there's no way for evolutionary escape. And in my research, I want to establish a pipeline to identify whether and which combinations of resistance mutations turn the polymerase inactive. So what's the point? If successful, my research method can be used to create mechanistic models of potential drug targets and then identify where drugs could bind and how they work, all from the comfort of my computer. Then the potential for overlapping inhibition can be assessed, and the drug development can focus on developing drugs that prevent evolutionary escape. This way, only one drug cocktail needs to be produced for every new virus and will always work. With such a cocktail, the next pandemic can come. Thanks for your attention.